So far, we have talked about the basic ideas of optimization, and also we discussed some gradient algorithms. Okay, and now we want to talk about Newton's method, which is not that popular in deep learning because when the number of parameters is large, then computationally Newton's method is not practical. But when the size of the model is small relatively, then always the Newton's method is on the table. So it is an attractive option. And also, even in deep learning, there are some papers talking about the Newton's method. So even though we don't use Newton's method that much, but still we have to understand the main ideas and the algorithms of Newton's method. Okay. So Newton's method is an iterative optimization method like a gradient descent method. Okay. For a two differentiable function. So the function can be differentiable twice. And it reflects the shape using the curvature information, which can be represented by a Hessian matrix, while gradient methods just follow the orthogonal direction to the contour. Here is an approximation and the learning direction. So basically, when we have an objective function, gradient is actually approximating this function with the linear model. So when we are here, we approximate this function with this line. And then based on this line, we know which direction is the way to go. So we know the left side is the right direction to minimize this function. That's how this gradient method works. And how about the Newton's method? So we approximate this function with the second order equation. So quadratic equation will approximate this f of w, and the quadratic function looks like this. And when we have a quadratic equation, then we know which one is the minimum. We have an equation to get the right answer. So from here, we can jump to this point directly. Since we are approximating this function more accurately, it is better than the gradient method. So in this case, it is just one-dimensional parameter space, so it's not easy to see the benefit. So let's take a look at this figure. We are here, and the gradient direction is always orthogonal to this contour. So we take one step, and this is not the smooth actually. So we take one step, and then we find another orthogonal direction from this point, and then we take another step, and then we have to take orthogonal, and then so this is how a gradient method works. Okay, but the Newton's method is using more information than the gradient information. This is not orthogonal. This one has some information about this shape. Newton's method actually approximates this contour with quadratic equation. And if this contour is similar to the quadratic equation, then it can go to this optimal parameter almost directly. But the problem is it is computationally expensive. In the beginning of this chapter, I actually discussed the Taylor series. We have f of w, and we want to approximate this f of w at time t. So this one is linear. So gradient method is based on linear approximation, and Newton's method is based on the second order approximation. So this one is gradient and this one is Hessian. And now we have the approximation of true function at time t. Look at this figure. We have the real function. Okay, so we are here. So at every location we have to approximate this f with the quadratic equations like this. And then we actually go to this point directly because we know how to solve this problem. So we trust this quadratic equation and we minimize this quadratic equation rather than f because we trust f hat is approximating f really well. Then we just trust this approximation and we minimize this approximation. So since this one is quadratic equation, then we know the solution. That's how Newton's method works. Okay, instead of minimizing f of w, we minimize f hat, assuming that the approximation is truthful. And to minimize f hat, we take a derivative of f hat. Okay, and then this is the derivative of f hat, and we set it to 0. Then this one is 0. We can rearrange the terms so that we have this one. So this one is parameter. This one is given. W sub t is given. The current parameter is fixed. And we calculate the gradient and we calculate the Hessian. And then we have to find this W. And that will be W sub t plus 1. This is the learning rule for Newton's method. This is it. You can actually think of this simple quadratic equation. So when we minimize this quadratic equation, we just take a derivative, which is 2ax minus b. Okay, and then we set it to 0. That's how we get this solution. X is b over 2 times a. So this one, a, 1 over a is actually a inverse is 1 over a. So this one is exactly the same as this one. This one is one-dimensional, but this one is in high-dimensional. Now let's talk about the Newton's method algorithm. Okay. Again, Newton's method utilizes the shape of function by Hessian. And given this learning rate and initial parameter, sometimes we don't need this learning rate, but sometimes we can use learning rate. And we repeat until stopping criterion meets, and we sample a mini batch and compute a gradient. So far, it's exactly the same as a stochastic gradient. And then we compute Hessian inverse, and then we update. Most of the time, epsilon could be just 1, okay? But we can relax this Newton's method. So when epsilon is not 1, if we use 0 point something, then it is relaxed Newton's method. Okay, that's it. And in gradient directions, the direction is orthogonal to the contour. Okay, so when we are here, then we actually move this direction, even though this is the best direction. But in Newton's direction, since we actually approximate this function with Hessian, which is about the curvature. Curvature is the shape of this function. So we know this direction is not the best direction when we are here. So this direction will move like this. So Newton's method knows the shape of this function. But there is some problem here. As I said, the computational cost is too expensive. Look at this one, H inverse. So when we have 10 parameters, then Hessian is 10 by 10 matrix. So we have to calculate the inverse of 10 by 10 matrix. Okay, so if the number of parameters is just 10, it's totally fine. But how about the deep neural network? Usually we have millions of parameters. Think about 1,000 by 1,000 matrix. Then we have 1 million parameters here. Just one single matrix has just 1 million parameters. Then 1 million by 1 million matrix. This is Hessian. When we have 1,000 by 1,000 matrix, then we have 1 million parameters. Then Hessian is 1 million by 1 million matrix. Then we have to calculate the inverse of this 1 million by 1 million. This is huge. Okay, so when we have a lot of parameters, this is not practical. And also the memory is another issue. And sometimes it might be unstable when H is not invertible. Then we can add mu times I. Okay, so Newton's method is really good in terms of direction, but computationally it's intractable. So there's another kind of alternative option here. Conjugate gradient descent. Okay, conjugate gradient descent is a gradient descent in a sense, but this one is used for Newton's method. Okay. So for Newton's method, what we need is to solve the system of linear equation, this. So from the previous slide, actually, we had this one. and this one is vector, it corresponds to B, and this one is a matrix, it corresponds to A, and this one is parameter. So this is what we need. We have to solve this problem. This one is coming from this one too. And the solution can be obtained by this one. It's just simple. When the A is invertible and the computation cost is expensive, that's why we talk about conjugate gradient. Conjugate gradient finds the optimum at most of these steps. So still, we are talking about these quadratic equations. Okay, so when we have a function, we approximate. Now we focus on just quadratic equation. We talk about f hat, okay, not f. And the CG conjugate gradient finds the optimum at most these steps. This is the dimension of the parameter vector. It approximately finds a solution with a few steps without A inverse. So look at this one. We start from here. Then the gradient method is in red and it takes one step. And then from here, the gradient method takes the next step like this. Because from this one, we have to take an orthogonal direction. This is orthogonal. Okay. And then from here, we have to take orthogonal direction and orthogonal and so on. That's how gradient method goes to this optimal solution. But look at this one. This one is in 2D. So conjugate gradient says we can find this optimal solution with only 2 steps. So from here, we move to this point. Okay, now we are here. And then conjugate gradient finds the optimal solution directly because conjugate gradient actually uses some information about A. So after taking this first step, considering the shape, the CG knows this is the next step. Okay, so we're going to talk about how conjugate gradient knows the right direction for the second step. Okay, first of all, we have to talk about conjugate vector set because conjugate gradient is based on the conjugate vectors. Okay, so 2 non-zero vectors u and v are conjugate with respect to A if u transpose A times v is 0. So it's like orthogonal, right? But we have A here. And given a mutually conjugate vector set, then let the solution of this equation be x star. And x star can be obtained by this one. So this one is a vector and the alpha I is the weight. So any solution, any vector can be represented as weighted sum of these basis vectors. Okay. Because in d-dimensional space, if we have a d conjugate vectors, then these vectors are basis vectors. So this optimal solution can be represented as the weighted sum of these basis vectors. And then alpha sub k can be obtained by this process. So since x star is the solution of ax is b, so ax star can be rewritten in this way because x star is here and we multiply a here, so this is ax star, and then we multiply p sub k transpose on the both sides, so we have p sub k transpose. Then if you look at this one is b, so now we have p sub k times b, and on the right side is the same. And now we have to use these conjugate vectors. So since these ones are conjugate vectors, which means pi transpose A times pj should be 0 when I is not j. Okay, this is the definition of these conjugate vectors. So in this case, I goes from 1 to d, but all the other pk transpose A pi will be 0 except this one. So when I is k, then this one is not 0. So from this, we got this weight. So a sub k can be calculated in this way. In summary, when we have a conjugate vector set, then the solution can be represented in this way. Okay. And then we have this one, but now we have to find out how to get this alpha sub I. So alpha sub I or alpha sub k can be obtained by this one. So which means when we have a conjugate vector set, then we know how to represent the solution as a weighted sum of conjugate vector set. Now let's talk about conjugate gradient descent algorithm. So in this algorithm, we have to build up conjugate vectors. So in the previous slide, we assumed that we have conjugate vectors, but now we have to find them out here. So this one is iterative method, and we start from x now, which is 0 vector. And in the previous slide, as you can see, x star, the solution is weighted sum of conjugate vectors. So as long as we have a conjugate vector p sub I, then we can calculate alpha sub I. So the question is, how can we get this p sub I? So when x naught is 0, then the p sub 0 is simply b minus a x naught. And then we're going to repeat these iterations until stopping criteria met. Okay. So first we calculate r sub k, so which is residual. Okay, what we want to do is actually this gradient should be 0. Okay, that's where the minimum is. So if x sub k is good enough, if x sub k is good parameter, then it will be 0. But if it is not, then there is a residual. That's r sub k. And the p sub k is r sub k minus the previous conjugate component. When we calculating p sub k, then we have p sub I when I is smaller than k. So in r sub k, we have lots of components, and we are eliminating p sub I from r sub k. And then x sub k plus 1 is x sub k plus alpha sub k times p sub k. Because as I said here, x star is sum of alpha I and pi. So gradually, we just add one component at a time. And then alpha sub k is simply calculated like this as in the previous slide. Again, in the previous slide, we assumed that the conjugate vectors are given, then we could calculate alpha sub k. But in this slide is about the conjugate gradient algorithm, so that we have to build up these conjugate vectors. Okay, and then gradually, iteratively, we add one conjugate at a time. So at the starting point, we just initialize x sub naught as 0 and the p sub naught as just difference between these two. And every time we calculate the residual, and from this residual, we actually eliminate all the previous components, and then there is a new conjugate vector. And then we add this conjugate vector with this alpha, and alpha is calculated like this. This is a conjugate gradient algorithm. And actually there is another, a better algorithm, more efficient algorithm, but the idea is like this. Okay, then how can we use this conjugate gradient for Newton method? Again, we have a function f of w, and we approximate this with the quadratic equation f hat. And then this one is quadratic equation, then the conjugate gradient can minimize this one. And in this case, when r sub k is small enough, then we're going to stop. Is it good enough? We are not exactly minimizing the function, the quadratic function, but that's okay because quadratic function is actually approximation of this f of w. So when we minimize this function, we don't have to minimize exactly because this one is approximation too. So as long as the minimization is good enough, the r sub k is small enough, then that's good. Then we move to the next point, and then we approximate one more time, and then we minimize f hat, and then we move, and then we do this again and again. That's how we use conjugate gradient for Newton method. Okay, again, this A is Hessian matrix. So far we have talked about the gradient method and Newton method, and then there is hybrid method, which is trust-reason method. So gradient method and the Newton methods are based on the approximation. And if the second order approximation is good enough, then we can trust the second order approximation, so we can actually go to the minimum of the quadratic equation directly. But sometimes we cannot trust a second order approximation. So trust region method is in between these two approximations, linear approximation and quadratic approximation. Okay, this is iterative solution. So in the previous iteration, if the quadratic approximation was good enough, then we can increase the trustness about the second order approximation. But in the previous iterations, the quadratic method is not working great, then we can reduce the trust region. That's why we call it trust region. So trust region will define how much we can trust this quadratic equation. So trust region method is actually in between these two, so that we can actually take the only good things from the gradient method and the Newton method, because the gradient method is stable but slow, and Newton method is fast but unstable. So trust region method is in between these two. Okay, so I'm not going to go through this algorithm, but if you're interested in, then you can study trust region method. And fortunately, we have a lot of good libraries for deep learning, like PyTorch and TensorFlow. In PyTorch and TensorFlow, there's automatic differentiation, so we don't have to calculate the derivative. We don't have to implement backpropagation by ourselves. What we have to do is to actually complete this computation graph. So when we have input and we have parameters, then we have to complete this computation graph and with this objective function. Then these libraries, they will apply their backpropagation, which was implemented based on the automatic differentiation. Okay. Then what is the automatic differentiation? So basically, inference in neural networks is just a sequence of operations and functions. So the chain rule can find the derivative based on this sequence. And this one is different from the symbolic differentiation or numerical differentiations. So symbolic differentiation is simply is what we do in the math class. We actually calculate the derivative. Okay, that is hard to find. But the Mathematica or Maple, they're actually based on the symbolic differentiation. And the numerical differentiation is like this. So when we explain the derivative, we use this equation. Then this equation explains the concept of derivative. But when we implement this one is approximation. We cannot have 0 here. Okay, so we cannot have this limit in the implementation. So when we have a small h, then that is approximation, not exact derivative. So there is some kind of error here, but automatic differentiation is correct answer. So most of deep learning is based on the automatic differentiation.